Hello grade 11 and grade 12 physical sciences learners. In today's video, we're going to be doing a past paper question, an exam question. Now remember, in grade 11, you learn about electricity, you learn about the different principles, you learn about EMF, you learn about internal resistance, and you're tested on it again in grade 12. So this video is for both grade 11s and grade 12s, and this is a tricky exam question. So both grade 11 and grade 12 learners, I hope you watch through the entire video for all my teacher tips and subscribe for more videos like this one. Let's jump right in. The first question gives me a circuit that looks like this with bulbs P, Q, and R. They say that they have the same resistance, identical bulbs. They're connected to a circuit with a battery of EMF E over here, negligible internal resistance, which means that we don't care about internal resistance in this question. There basically is none in this question. And they ask me the following questions. How does the brightness of bulb P compare with that of bulb Q? Choose from equal to, greater than, or less than, and give a reason. Now, before I get into the answer, I just want to remind you that brightness of the bulb has to do with the power of the bulb. And remember, we can calculate power, P, with multiple different formulae, and the power depends on a number of different variables, namely the potential difference across the bulb, the current through the bulb, and the resistance of the bulb. So what I've done over here is I've pasted the formula sheet, the data sheet that you will receive in your paper 1. This can be found in the grade 12 exam guidelines, but grade 11s you'll receive the same formula. I'll link it in the description box below, the exam guidelines if you want to see it. And because we're working with brightness, which bulb will be brighter, we need to look at power. And here are the different power formulae. So as I've mentioned, power depends on the voltage or the potential difference across the bulbs, the current flowing through them, and the resistance. So when comparing bulbs P and Q, we can note the following. They are identical, so the resistances are the same. Because they're connected in series with each other, P and Q are in series, the current that flows through them is the same. And because they're identical and they're connected like this in series, basically what it means is that the voltage across them will be the same. The potential difference across them will be the same. So therefore, the brightness of bulb P compared to Q is equal to. And the reason is because they have the same resistance, same current, same potential difference. So if I had to work out the power of each of these bulbs and say I had to use this formula over here, P equals V squared over R. V is the same, R is the same. Even over here, I is the same, R is the same. So that is why. And where a lot of students go wrong is they say, but ma'am, isn't voltage the same? Or they get confused with a parallel series connection. So I just want to explain it to you quickly because this could be very useful maybe in another question. If the EMF of the battery, let's just give it a number. Let's pretend the EMF of the battery is 20 volts. What that means is that this branch has a potential difference. If I have to connect a voltmeter across this branch will have a potential difference of 20 volts, which means if I had to connect a voltmeter across resistor R, it would have a potential difference of 20 volts because it's the only voltmeter in that branch. What it also means is the top branch, which contains P and Q, that potential difference across that branch will be 20 volts, okay? It doesn't mean that P will have a potential difference of 20 volts and Q will have a potential difference of 20 volts. And a lot of students say, but ma'am, everything's connected in parallel. So isn't voltage just the same for everything in parallel? Voltage is the same for parallel, but when we say that, we mean the voltages of the branches are the same. So, because the battery is 20 volts, there's no resistors connected here in series. What that means is that the parallel connection gets all of those 20 volts essentially. So this branch, the first branch, will have a 20 volt potential difference, and so will the second branch have a potential difference of 20 volts, okay, 20 volts. But there's 2 resistors in that branch. So each resistor, because they have an equal resistance, will share that potential difference because voltage splits or potential difference splits in series. So the branch is 20 volts, 20 volts, 20 volts because those branches are in parallel. But in the top branch, which has a total potential difference of voltage of 20 volts, we've got two resistors. They're equal in resistance, so it'll be 10 volts, 10 volts. I hope that makes sense. But in this question, what I'm trying to tell you is that it doesn't really matter what their values are. P and Q, same voltage, same current flowing through them, same resistance. So therefore, they will shine with the same brightness, same power. Next question, how does the brightness of P compare with that of R? We have to choose from equal to, greater than, or less than, and give a reason for the answer. And in this case, the brightness of P, this one over here, will be less than the brightness of R. So your answer is less than. So what I mean is this one will shine less brightly than this one. And the reason why is because although they have the same resistances, so R is the same, remember we discussed the fact that P will basically have half of the voltage of R. Okay, so your reason is resistor P has half of the voltage of resistor R. Okay, or R has double the voltage of resistor P, which means that the power, therefore the brightness, will be more for R, less for P. There we go. So if P has half of the potential difference, V will be smaller, therefore P will be smaller, the brightness will be less. Now moving on to this circuit, which is quite complicated. Don't go anywhere because later on we're going to get into quite an interesting question, a 6-mark question, this one over here, which is quite difficult, and you don't want to miss the last question over here, which is always going to be asked in your test. It's an explanation question. So let's read the story first. Always read the story, look at the diagram, fill in any important missing information. So it says a battery with an unknown EMF. Okay, so we don't know the EMF. I'm going to put EMF with a question mark. And a negligible internal resistance, which means I don't care about the internal resistance, is connected to 4 resistors, a high resistance voltmeter, 2 switches, here's the one, here's the other, and 2 ammeters of negligible resistance. Both switches S1 and S2 are closed, and when this is the case, the reading on A1 is 1.2 amperes. Now, the first thing that I just want to show you, and you also need to orientate yourself when you get a circuit like this, is where's the parallel stuff, what's in parallel, what's in series. So if you start at the battery and use your finger to follow along the main line of the circuit, this is total current, total current, total current, total current, total current, all the way till there's a split in the wire. Same thing here. So A2 will read total current. Total current, that is important just to know. Then as soon as we get to this over here or this over here, there will be a split in the current, because as we know, current splits in parallel. So some of the current will go through this branch. Okay, and that is what A1 will read. So A1 reads the current that goes through the 2 ohm and the 5 ohm. The 2 ohm and the 5 ohm are in series with each other. The same current goes through those. Then the rest of the split current goes through this branch over here through the 3 ohm. So basically what's happening is a circuit that looks like this. Some people prefer to see the circuit looking like this. It's maybe a bit easier for them to understand. So you can see total current goes through resistor R with an unknown resistance. Then the current splits. Some of it goes through the 3 ohm up there. And then the rest of the current goes through the 2 ohm and the 5 ohm over here, where the current joins again, and then it becomes total current going through A2. The first question says, calculate the reading on the voltmeter. Now, the voltmeter is connected just across the 3 ohm resistor. So to calculate a reading on a voltmeter, we're looking for V. We do know R. R is 3 ohms. But do we know the current that goes through this branch? Do we know the current that flows through this branch? Let's see the story again. We have the reading on A1 is 1.2 amperes. So there's A1 over here. Now, please don't make this mistake. A1 is calculating or is reading the current going through the bottom branch. Okay, so A1 is not the current that flows through the 3 ohm. So I can't use this information over here. However, what I can do, because they give me the current that goes through the bottom branch over here, I know the current that goes through the green branch. I know that current. That current, let's write it over here, that current is 1.2 amperes. Do I know the resistance of that branch? Yes, I do. It's 5 ohms plus 2 ohms, which is 7 ohms. And that allows me to calculate the voltage. And you might think, okay, cool, ma'am. I don't want the voltage of the bottom branch though. I want the voltage of this voltmeter. But remember, these branches are connected in parallel. So what that means is the voltage across the green branch is the same as the voltage across the pink branch. So if I know the voltage across the entire green branch, it'll be the same as the voltage across the pink branch, and the only resistor in the pink branch is this 3 ohm resistor. So basically, what I'm trying to say is if I calculate the voltage across the green branch, it is the same as the voltage across the 3 ohm resistor. I hope you are with me on that one. That can be quite complicated for people to understand. But if I know the voltage across the green branch, it's the same as the voltage across the pink branch, which is basically the voltage across the 3 ohm, because the pink branch and the green branch are in parallel, and voltage is the same for parallel connections. So I've got the current, I add the two resistances together to get me the total resistance of the branch, and I use V equals I times R, and I get 8.4 volts. My next question says calculate the reading on A2. Now remember we discussed earlier that A2 over here is reading the total current. A2 reads the total current. So remember, the total current is equal to the current in the green branch, which was given to me. This was 1,2 amperes, plus the current in the pink branch, which I don't know. So what I need to do in order to find the answer for A2, which is the total current, is I first need to work out the current in branch 1. I've called it branch 1, the pink branch. And then I add it to the current in branch 2, which was given to me, and then I can get my answer. So what I'm doing is I'm writing here that I'm working out the current in the 3 ohm, or the current through the 3 ohms, is equal to V divided by R. That is a formula that you get on the formula sheet. It's this one over here, just I've rearranged it. I is equal to V over R. Remember the voltage over here we calculated in the previous question. It was 8,4 volts. So 8,4 divided by the resistance, which is 3 ohms. And I get 2.8 amperes, but remember that's not your final answer. That is the current through branch 1, so 2.8, and the current through the other branch, the green branch, is 1.2. Therefore, total current, I'm going to write I total, or you can write the reading on A2 is equal to 2.8 plus 1.2, which is equal to 4 amperes. If you don't put your unit, you will get the question wrong. And that is where you get your marks for this question. And just to go back for the previous question, it's formula, substitution, answer with units. 8.2.3 wants me to work out the power dissipated in the 3 ohm resistor, which is this one over here. Now remember, we have resistance, we have the voltage or potential difference across the resistor, we even have the current. So when it comes to working at power, we have a lot of different options of formulas that we can use. So we could pretty much use any of these formulae, and let's go, let's do it. So I've chosen this one, formula first for a mark, substitute for a mark, and then answer, but you have to have a unit. So power is measured in watt, W. No unit, no mark. But just to show you all the different options that you could have potentially used in order to get your 3 marks. Now for the difficult 6-mark question. So this would be a level 4 question, very challenging, problem solving, but we're going to break it down and I'll show you that it's not that bad. So we say switch S1 is now opened. S2 remains closed. Remember, initially both switches were closed. So if you read the original story, it says both switches are closed and they give me a current reading. And we also worked out the total current for that question. Then they open one of the switches and they give me a new current reading. And the new current reading that they give me is for A2, and that once again is still total current. So what happens in the second scenario over here is switch S2 is staying closed, S1 is opened. So when we open S1, what essentially happens is we are breaking the circuit connection over here. S1 is opening. It means that this branch is no longer functioning. What that technically means is we now have a complete series circuit. So total current will flow through here, will flow through there, there, and back to the battery. It does not go down the second branch because that switch is open. Current won't flow through there. Because they asked me to calculate the EMF of the battery, you may think that you need to use the following formula, which includes EMF over here. You can see over there, EMF equals I brackets big R plus small r. But remember, small r is internal resistance. And in this particular question, we know that the internal resistance of the circuit is negligible. Remember, they said that right at the beginning. Said over here, the internal resistance is negligible, which means that there's no internal resistance. It means that we don't count internal resistance. It means that we don't need to use that formula. But what do they mean then when they say EMF of the battery? Remember, the EMF of the battery can also be known, or you can also think of EMF of the battery as basically the voltage across the battery, the potential difference across the battery. Because there's no internal resistance in the battery, the EMF of the battery's voltmeter, if there were voltmeter attached across the battery, it would read the EMF whether both switches are open or closed, basically. It's a total voltage across the battery. But there are basically two circuits going on here. Situation one, when both branches are important in the circuit and both branches are functioning. Then we have a certain total current when both branches are operating. And then there's a second version of the circuit where one branch no longer is operating and only this branch is operating. So I hope you kind of see where I'm going with this question. We're going to end up having two equations, and it's going to end up being kind of like a simultaneous equation. Let me show you what I mean. If I were just to try and use the circuit as you see it over here without the second branch, and I ask you to calculate the voltage across the battery, which is basically the EMF of the battery. I'm asking you to calculate what is the potential difference, what is the voltage across the battery. You'll say to me, okay, cool, ma'am, well, there's this one over here, this resistor over here, which has a certain voltage, and then this resistor over here, which has a certain voltage. If I add this voltage plus this voltage, it'll give me the voltage across the battery, because remember, potential difference splits when resistors are connected in series. So basically, this voltage over here plus this voltage over here will equal this voltage across the battery. Okay, cool. Then we'll be able to answer the question. Let's see if we can do it. How do I calculate this voltage across the 3 ohm resistor? Remember, this branch is no longer existing. So it says that when the switch is open, okay, this branch is no longer existing. The reading on A2 is 3.48 amperes. What that means is, in order to calculate this voltage here, I'm going to draw an arrow so you can see what I'm doing. V is equal to I times R. The voltage across this 3 ohm resistor over here is equal to the current, which is 3.48 amperes times 3, because you just need to keep reminding yourself that it's now a series circuit. So the total current, so the current on A2 will flow through this 3 ohm resistor back to the battery. So there we go. 3.48 times 3, that's cool, we can do that. I get 10.44 volts, but I still have to work out the voltage across this resistor over here. Now, how can I do that? Is it possible to do that? No, because V is equal to I times R. We know the current. We said that the total current will flow. 3.48 amperes flows through the entire circuit. So yes, we know the current, 3.48. But do we know this resistance? No, times R. So now we reach a point where we're stuck. What we have at the moment is that the EMF, or the voltage across the battery, is equal to 10.44, which is this voltage here across, I know I'm scribbling a lot on this page, so it looks a little bit chaotic, but the 10.44 is the voltage across this resistor over here, and then we can say plus 3.48 times R. This is basically the voltage, this part here is basically the voltage across this resistor. But I can't get an answer now. How can I get an answer if EMF is unknown? That's what I'm looking for. And R is unknown. So what I'm going to have to do is I'm going to have to look at the previous circuit, the previous version of the circuit, when both switches were closed. and I'm going to have to create another equation for EMF. So for this version of the circuit, when both switches are closed, remember, as soon as both switches are closed, we have this parallel circuit here, this parallel combination. So the total current splits. We have a parallel circuit now because both switches are closed. So the EMF across the battery, the total voltage across the battery, will equal to the voltage across this resistor over here, voltage across R, plus the voltage across this parallel combination over here, which we already know. Remember, it was 8,4. So we can fill it in like this. We can say, okay, the EMF is equal to the voltage across the parallel part, which is 8.4. We worked that out in previous questions, plus the voltage across R, which is basically equal to your total current, which in this case was 4 amperes, times R. Or you could just leave it as VR. Okay. And I just want to emphasize, because I know students are going to get confused and they're going to ask me, how did I know that VP, voltage across the parallel, is 8.4? Because remember, we worked out the voltage right in the beginning. We worked out the voltage in the green branch was 8.4, which means the voltage in the pink branch over here is 8.4, which means that overall, the voltage for this part of the circuit is 8.4. So essentially, it's this 8.4 plus the voltage across this resistor. Those two added together will give me the EMF of the battery, or the total voltage of the battery. So now we have two equations. We have one equation when both switches are closed, the original scenario, that's my equation, and one equation where one switch is open and it becomes a series circuit, that is my equation. And now we do simultaneous equations. So this is how it works. Because both equations are equal to EMF, you see this one equals EMF, that one equals EMF, or instead of EMF, you can write it as V battery. So the voltage across the battery, it doesn't matter what you call it, voltage across the battery. But because both equations are equal to the same thing, we can make the equations equal to each other. Or you can think of it like this. EMF is equal to this. So in the place of EMF, I can put all of that. Essentially, what we're going to have is this. Both equations being equal to each other. This is simultaneous equations. You should have learned this in maths. I think the easiest way to think about it is both equations equal EMF. So therefore, both equations can equal each other. And then I can solve for R. Once I solve for R, then I can put it back into my formula to get EMF. So let's do it. Let's solve for R. How does this work? R is my variable. It's my unknown. So I get all the R's to one side. I'm going to go 4R, stays on this side. 3.48R comes over, minus 3.48R. On this side, I've got 10.44, stays on this side. This is plus 3.48. It becomes over, becomes subtract. 8.4, inverse operations. So I get 0.52R. Remember, R is your variable. It's what you're solving for. Last step. Take 2.04 divided by R. So whatever's next to the variable goes at the bottom. That's how I remember it. 2.04 divided by 0.52. That gets me R. So R is therefore equal to, I get 3,923076. Don't round off. Okay, so I'm saying dot, dot, dot. I'm keeping it on my calculator. Don't round off. That's measured in ohms. Because I am not at the end of the question. Remember, the end of the question is what is the EMF? I've got R. But now that you have R, you can pick one of your formulae, because look at your formulae that you created. This one, these ones over here. The formulas for EMF. They both have R in them. So you pick one. I'm going to choose this first one over here. EMF is equal to 8.4 plus 4R. In the place of R, you put what you just found. So 4 times that whole number over there that you just found, 3,92 dot, 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 dot. You work it out in your calculator, and I get 24,09 volts. This is a very difficult question, level 4. So it helps, it forces you to think outside the box. You have to work with simultaneous equations. You have to work with two different versions of the circuit. But take it step by step, look at what you have and what you need, and hopefully it's not too bad. Our last question is an explanation question. So they say that S2, the switch, is opened So this switch is opened, this branch no longer functions, it's no longer a parallel circuit, it's now a series circuit. S1 is closed. How will the reading on A1 change? Now, A1 is effectively measuring total current. So we are asking you, how will the reading on A1 change? What will happen to total current? What will happen to the current that flows through this part of the circuit? Now, to know what happens to current, we always need to consider what will happen to resistance, total resistance. And this is how I remember it. If you're taking a resistor out of parallel, okay, so that's basically what we're doing. We're opening up a switch, we're removing a resistor in parallel. It seems like it's backwards, but if we remove a resistor in parallel, total resistance increases. This does confuse students. It seems like it would be the other way around, but the reason why is because, remember, total current originally flows through here, here, and here, and then it splits when it gets to these parts of the circuit. And when it splits, what usually happens is some of the current flows through the one branch, the rest of the current flows through the other branch. So basically, the current has two options. It's easier for the current to flow when there's multiple options. Think about if there's two roads leading to the one destination or one road. It's a lot easier if there's two roads, there's more options, easier to flow, as opposed to having all the cars in one road. Okay, so what we're doing when we're opening the switch is we're eliminating a road. All the current is forced to flow through that green part of the circuit, which means it's more difficult to flow. Total resistance increases. And as soon as total resistance increases, total current decreases. They are inversely proportional. If voltage is constant, so the voltage across the battery, if that's constant, which it will be. So the answer is actually decreases. And your reason is because when we open S2, the total resistance increases of the circuit, therefore the total current of the circuit decreases. So that's how you would write it, and I would always just add in if voltage is constant. And just as a side note, this is where you would get your marks for the 6 marks question. Just note that their answer differs slightly from mine because they rounded off here, which you should not do. In your final exams, you are not allowed to do that. So this 3,92, on my calculator, it wasn't 3,92, it was 3,92, some 6, 7, whatever. It went on and on and on and on, and that's not the end of the question. So you need to use the unrounded off version here, which gets you a slightly different answer, but my answer is more correct. That is how they mark in matric finals, so please don't round off till the end of the question. I hope that this has been helpful. Please subscribe for more videos like this. Comment down below what you want to see next, and I hope to see you in another video very, very soon. Bye, everyone.